let's make a start. Screen shares up. Yes, cool. Okay, so as per the Class 2 curriculum, we're currently up to basically the end of the quadratics stuff on that, and moving into some of the intro to polynomial stuff. So, I mean, as before, I'll basically deliver the class as if it was the curriculum. If it's just going to be, yourself and myself, we'll go back to what we're doing before. Cool. Okay, so sketching quadratics. Couple of ways you can go about it. In fact, I think we could probably consider 3 main ways of going about it, one of which is the turning point form. So you can complete the square on a quadratic to get it to look something like this. The benefit there being that you can very easily read off where the turning point of the quadratic is going to be. So you've got this h and k term, which tells you both the horizontal and the vertical component of where that turning point would be. Basic quadratic, parabola, dilation factor, you'll have this sort of multiplier at the front, which will essentially dilate the function. It'll stretch it in a particular way. Bigger number means it becomes narrower, so it shoots up the y-axis faster than it otherwise would. And smaller numbers, approaching 0, I should say, don't go into the negatives. That's when you get into reflections. But smaller numbers approaching 0, those are going to make it wider. Or in other words, it's going to stretch along the y-axis slower than it otherwise would if it was just basic x squared. This is where the negatives come into play. Negatives are in fact reflections, so instead of it pointing directly up, it is now going to point directly down. Doesn't really exist in the sense for reflecting about the y-axis, simply because the quadratic is in fact symmetrical already about the y-axis, and that's also supported by the algebra that's underneath. So you can see if you were to put a negative sign directly on the x spot, the square is going to cancel it out. So the algebra also shows us that whether it's positive or negative, you're not going to get any actual change. That's what I was touching on earlier. The h term you can think of as a horizontal translation. X minus h is going to move the quadratic to the right. X plus h is going to move it to the left. So whatever the number is in that bracket is going to correspond with what the x-axis, or what the x-coordinate is of the turning point. Just again, keep in mind the difference. The plus becomes minus. The plus is a shift left. The minus is a shift right. Vertical translation has no such issues. You can just read it directly off. So this one has a +1 on it, so it's going to go up by 1. This has a -2 at the back, so it's going to go down by 2. As we get into more of the transformations side of things, we'll start to see why there's that sort of weirdness that goes on with the flip in the horizontal, but not true in the vertical. So, sketching quadratics, fundamentally you just need to know where are my axes intercepts, where are my endpoints, if possible, and where's my turning point. If I can dot out all of those things, I can very easily just draw a line that connects all those points in a smooth curve. One of the first ways you sketch quadratics, or you get introduced to sketching quadratics, is using the turning point form. So you'll have to complete the square to achieve this if you are in the standard polynomial or standard quadratic form. So typically speaking, you wouldn't go out of your way to complete the square on this if you weren't forced to, because it takes time. All right, there are going to be faster ways of working from it in this position. I'm just showing you what you would do if you had to do it. So if you had to complete the square or solve it via turning point form, then I have it written out as an actual formula, completing the square. There is a sequential way of doing this, although I find it's a bit hit or miss. Some students get it, some students don't. So I've kind of just taken the approach of, well, you kind of already need to memorize the quadratic formula. This is very reminiscent of the quadratic formula. In fact, it is basically just a rearranged version of the quadratic formula. That's actually how you get to that formula in particular. So whether you prefer to do the methodical approach to it, where you do a multi-step process to complete the square, or whether you just want to use an equation like this, they're the same thing. It's up to you. Yeah, so you go through, you complete the square, And as soon as you complete the square, the first thing that is available to you is where the turning point is now going to be. Remember, the plus, the horizontal term, is going to flip its sign, and the vertical term is going to maintain its sign. So you can see it's a shift left by 3/2 and a shift down by 1/4, hence giving us the turning point for that one. From there, going to calculate the axes intercepts. You do this the same way every single time. Set the x value to be 0 for the y-intercept, and set y equals 0 for the x-intercepts. Now, depending on the type of graph you have, the actual arithmetic of achieving that might be more difficult. Like for instance, when you get into quadratics, you're starting to play around with these plus minus square root terms, but still fundamentally you're always starting it off the same way. Shove in x equals 0 or shove in y equals 0. Gonna get us those, and then yeah, just draw the curve connecting all those points. Point, 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 point. Very easy to just draw a parabola. You don't even have to think about what direction it's going up or down. Now it should be relatively easy to spot whether it should go up or down. That'll be part of your error checking. If you're looking at that lead term, the x squared term, and it has a positive in front of it, it should go up. So if you join your graph and it goes down, well, that's a red flag for you to try and fix up any arithmetic you've done there. If you do have a restriction on the domain, so for instance this one here says we are going from -3 to 1, exclusive of the 1, we're just going to sub in those x values to get what those corresponding y values would be. So you sub in x equals -3, you're going to get y equals 2. You sub in the x equals 1, you're going to get y equals 6. When you actually draw out those endpoints, just keep in mind the difference between inclusive and exclusive. Inclusive, you're going to use a dark circle, and exclusive, you're going to leave a gap in the middle. You're going to leave a white circle there. That's one way of sketching quadratics. Any of that need to be clarified further? Okay, factorization. So this is probably one of the fastest ways you can sketch a quadratic and even solve a quadratic. If you can very quickly find the factors, if they exist, because they won't always exist, or at least they won't always be very easy to find. No, actually I'll take that back. They may or may not exist. Sometimes you have no solutions. Point is, if you can find the factors really quickly, so just doing the add together times together method, for instance, multiply out to give this, add to give this, you can create your two factors and essentially just using null factor law to find your x-intercepts, which is very trivial, right? You just take each term and make it its own separate equation, setting y equals 0, because if you have two things multiplied together, that gives 0. One of those terms or multiple have to be 0. Y-intercept, just x equals 0 once again. Turning point is slightly easier from here. Instead of having to go through a full complete in the square, one thing that's unique to quadratics and no other graph, maybe the circular functions, is that the turning point is in the center of its x-intercepts, always. Cubics don't quite do this. They have a bit of a lopsided peak to them, so you can't quite just use the midpoint of these. But for quadratics you can. They're always symmetrical. So we're just going to use a midpoint to get that x value. There is still the fact that we need to find the y value as well with that. So turning point form would have also given us y. Yeah, there's pros and cons. But yeah, just getting the y value. And then again, this is the exact same graph, just solved a different way. So basically, when you're given a particular form of the quadratic, probably best to stick with that form, depending on how much effort you want to put into it and depending on what methods you are comfortable with. Ideally, you'd be comfortable with all of them, so you can save time on not needing to convert it to a particular form before using it. But yeah. Any questions on factorizing approach? Easy. Next up, quadratic formula and the axis of symmetry. So you can always solve the x-intercepts if they exist with the quadratic formula, no matter what. And yeah, quadratic formula. If you haven't memorized it by now, you do need to have this memorized because it's useful for a lot of quadratics, especially when it gets into the stage of square root solutions. You really not want to be doing the complete the square and then rearrange for x. That'll take a lot longer because you'll be essentially creating your own version of the quadratic formula and then rearranging it afterwards rather than just having it from the get-go. You know, if you're already doing this, you don't need the axis of symmetry anymore. Again, you can just do the midpoint of these two things, but I'm just highlighting it there just in case you, for whatever reason, prefer that equation. So x equals negative b over 2a, you'll actually see that exists in the quadratic formula there, negative b over 2a. This plus minus term is essentially like a little offset of that middle point. Right? You're plussing a root, you're minusing a root either side, which is why the midpoint is always just negative b over 2a. But again, if you already have them, you just don't need to do this. You can just do the midpoint again. Those are the main tools you have access to there. Typically, fastest is going to be a factorization approach if you can find the factors. Your next best bet is probably going to be using quadratic formula to get your x-intercepts. If you already have it in turning point form, obviously just use that. If you already have it in factorized form, obviously just use that. But if you're stuck at the basic quadratic polynomial form, these are the things I'd probably be considering. Anyway, that's those. Any clarifications there? Okay. Next up, we're going to have a look at some more generic polynomial stuff. So you might have heard me refer to the quadratic as a polynomial a couple of times. Well, that's because it is. It's part of this family of functions that are x to the power of something, of which the quadratic is just x to the power of 2. In methods, we start looking at a lot higher power terms. They don't usually go further than like x power of 4, although you can use the lessons learned from x cubed, x power of 4. You can use those lessons to extrapolate to what the other bigger power functions would now look like. One of the challenging things that you get hit with right out the gate is polynomial division. You typically don't really use this in exams. Yeah, do we ever come across this in exams? I don't think so. This is more of a SAC thing that they'll throw in at you, and probably closer to Unit 1 and 2 rather than Unit 3 and 4. This is a method to factorize polynomials. Granted, initially we kind of have to already know what the factor is. We'll look at ways to actually find what that factor is in the remainder and factor theorem section of the lecture. But for now, what we're essentially doing is trying to figure out how can I perform a division between a polynomial and, I mean, usually we do linear. That's what is normally going to be the case. The book will also show you ways of performing it with other polynomials as well. It's the same procedure, but you typically only use it for linear. These are the steps all outlined. That's a bit of a mess though, so let's have a look and see what those steps actually look like in an example. So our goal is to simply just make this not look like shit. So starting with the polynomial division approach, we look at the divisor. That's going to go on the outside over here. And then we look at the numerator of that fraction. That's going to go on the inside here. From there, we look at the two highest order terms. So that's going to be the x cubed in this case and the x over here. What's the term that has the biggest power attached to it? Then we just divide one by the other, specifically the inner divided by the outer one. So x cubed divided by x is going to get you x squared. That result I'm going to put directly above the just above on that line there. From there, once you have that result, you take that result and then multiply it by the entire left-hand side. So you're not just hitting this again, you're now also hitting this one. X squared times x is going to get you right back to x cubed. This should always happen. There should always be a mirror of that leading term, otherwise something's gone wrong. And then x squared multiplied by 2, 2x squared. You should be able to do most of this in your head. If for whatever reason you can't, feel free to just put that on the other side, like to the right of your working out. There's nothing wrong with doing that at all if you're just learning this for the first time. From there, you perform a subtraction. So you take the thing that's here and you subtract the thing that's below it. That's pretty much it. If you've set up your grid good enough, you can just go basically vertically down like you would for very basic when you learn subtraction for the first time. Probably you would have done like table method. So you do x cubed minus x cubed, which gives you 0. And then you do x squared minus 2x squared minus x squared. These are all considered zeros, so you just do something minus 0 gives you that exact same thing, and so on. I'll point special attention to the way I've written this. I prefer to put brackets around the full thing and the minus over here. The reason why is because by accident, people are going to go x cubed minus x cubed, and then x squared plus 2x squared. We don't want to be doing that. So I'm going to make it to myself as obvious as possible that that minus hits everything. It's a very common mistake to just look at this term, be like, yep, do that. Not quite. You want to have this there. That's the 3-step procedure, more or less. Divide the two terms, get your result, chuck that result through here as a multiplication, and then perform a subtraction. What you'll be left with is a polynomial that is when you're dealing linear, you'll have a polynomial that has one less power than what you started. This was x cubed, this is now x squared. From there, we take this as the new starting point and do the exact same thing that we did before. Minus x squared divided by x. So again, this is the biggest power term over here. This is the biggest power term over here. Do that division and put that in the next spot on the top. Then take that result, multiply through, and put that down. Oh, sorry, over here. And then the subtraction. So again, I'm going to wrap those in brackets, put a minus sign, and then do that subtraction. Again, you'll see that the leading terms will always be identical, no matter what. So whenever you do this, you'll always have 0 underneath for that subtraction. Again, the brackets, especially when there's like negatives and stuff going on here, can be kind of confusing. So when you read this, you just go minus 14x minus 2x. Double negative cancels to a positive. Cool. Now I get what I'm doing. And again, you'll see you've shrunk it down a little bit more. Do that whole procedure again. And if you started with a factor, so x plus 2 was a factor of this cubic, you'll always get 0 at the end here. If you have something that's not 0, if you have like a single digit left over, that would be considered the remainder, which we'll have a look at in a bit. Why have we done this? Well, what we've essentially said is we've been able to split this cubic up into a quadratic term and a linear term. Those two are factor pairs of this full cubic. So in other words, if you perform this division, you get that. All I have to do is multiply both sides by my denominator, and I've converted my cubic into a factor pair. And that's good because if you remember from when we're touching quadratics, now null factor law plays a role. You've got two things that are in brackets multiplying each other, and if you're trying to find the x-intercepts, well, you just shove your y equals 0. You have null factor law to work with now. Whereas otherwise, if you just got this massive cubic, there's no like cubic formula like there is a quadratic formula. So this is the next best thing that you've got access to. Cool. All right, that's the procedure there. We're going to have a look at another example briefly with the quadratic factor. or I guess the quadratic division. Anything to clarify before going into that one? Because this is probably the hardest thing of all polynomials, I would say, getting your head around the polynomial division. Everything else is kind of like what you're probably already used to, algebra style. Cool, all right. But there's no major concerns. Whether you have a quadratic here or literally anything else that's a polynomial, you're still doing the exact same procedure. The only thing I'm going to note is that, obviously, when you perform this division, things are going to escalate rather rapidly. So instead of going from x cubed down to x squared, you're now going down to x. So all of a sudden, after you've done one loop of the thing, you've now got this sort of mismatch of where the things are being placed if you're just going left to right. I've still put them left to right like that. One thing you might consider doing is putting in like a 0 in this spot and then putting in the term that you should over here. That way you can keep that verticality. But you'll find most textbooks do this, so I just wanted to get you used to what that would actually look like when you're looking at your exam. When you're looking at the solutions in the textbook. Point being is the thing is going to decrease rather rapidly, and what you'll actually find is your remainder term is now going to start looking a bit weird, potentially, depending on your starting point. When you start here and try to do the arithmetic, the whole procedure, you're going to notice you start with minus 15x and you're going to divide by x squared. That doesn't quite work out because what you're left with is a fraction, which technically nothing wrong with that. You can do that, but it kind of defeats the purpose of what we're trying to do. We're going to stop before we get into fractions in this spot. The quotient is what it's called. So this actually becomes our remainder term, even though there are still x's in there. It's still considered the remainder of that division. So how do we handle remainders? So whatever this looks like, doesn't matter what it looks like, it is the numerator, whatever that is the numerator, and what's the denominator is the thing that you were dividing by initially. So we had x squared plus 1 over here. That's going to be the denominator of that remainder term. Effectively, we're just saying this is the bit that I couldn't cancel out the factor from, and so it's got to still have that division in there. And this is the bit that I could get rid of, the x plus 1. So if you have a remainder, it's not super helpful when you're trying to solve a polynomial, but it's more so this is more theory stuff, and when you start looking at remainder and factor theorems, specific questions, which is the next module. Ideally, you want to get it to a stage where you have a perfect factor like that, so you can get your two multiplications going. Anything to clarify from that? All right, I said it a couple of times, remainder and factor theorem. What the hell am I talking about? Well, we just looked at a nasty procedure, and sometimes we got a remainder at the end. If all you're looking for is the remainder at the end, then you can ignore that entire procedure and use the remainder theorem equation. So basically put, whatever polynomial you're trying to divide is considered f of x. So for instance, in this case over here, f of x will be considered the numerator of this bit. This is the thing you're trying to divide. And the a and the negative b are going to come from the linear that you're dividing by. So key point there, this only works for linear division. So for instance, x plus 2 will be the linear. You would have an a equals 1 and a b equals 2. Just keep in mind that this one wants a negative b. So if all you do is find your a and your b, chuck that into the remainder theorem equation, so your polynomial, whatever you get after simplification is the remainder. And that arithmetic is significantly easier. It takes 4 lines as opposed to 4 pages, or at least 4 pages of pictures on my thing. You're not going to quite write 4 pages of working out for one question. That would be Tragic. Yeah, so let's have a look at an example. So it's the same thing actually. Nah, different. Cool. So this is the way a kind of question like this will typically be worded. Find the remainder after dividing this by that. F of x is fairly obvious. It's just the thing you're trying to divide. The a and the b you might get a little bit tweaked out by. So one of the things I'll typically do is just say, okay, I have my generic linear ax plus b, and that is the linear that I have. And so from there, you can very quickly look at what those coefficients should actually be. A equals 1, b equals -2. Chuck it in, simplify. This is just arithmetic. This shouldn't be anything crazy. And that tells us that if I were to do the whole polynomial division procedure, the number at the very bottom would be 6. Any questions as to that? There's a few applications of it in the textbook or otherwise. Probably even this. Actually, I think we did have a couple of exam questions that use remainder theorem in them and factor theorem. If I were to take a stab at the memory, I think it's like multis usually they'll come up in. But anyway, so in this case, we're told that the cubic that we have has a remainder of 17 when divided by x minus 3. We'll notice that this polynomial isn't fully solved. There's this further coefficient in there, and our goal is to figure out what that coefficient would be. As soon as you're given information about the remainder, it should be a light bulb in your mind to say, hey, maybe the remainder theorem should be helpful here. So we're going to go through the exact same procedure we did with the remainder theorem. So the linear to give us our a and our b terms, the cubic, the polynomial that we have, whatever it is going to be our f of x. Chuck it into the remainder theorem equation, so -b over a, and simplify. Now, if you're just doing the simplification, you're going to get to 3k plus 5. Just keep in mind that we're actually told what the remainder should be. That actually completes the equation. We're able to put that equals 17 on there because we know the remainder should be 17. This is an equation with one variable. You can very easily solve for k. Factor theorem is basically the same thing. So I talked about this earlier, which was we would get a result of 0 if the linear we chose was a factor of the polynomial we tried to divide. That's what this says. So if the remainder theorem gives you a remainder of 0, what you have is a factor. So very basic example that the book will try to get you to do. Prove that something is a factor of some other polynomial. All you're trying to do is use remainder theorem and prove that your remainder theorem turns out to be 0 after simplification. If you get 0, good, you're happy. If you don't get 0, you say false. X plus 1 is not a factor. It wouldn't be worded like this if it could be false. They'd probably say something to the effect of determine if x plus 1 is a factor or not. Yeah. So this is all now leading into how do we now handle things like this, where I'm not actually told what the factor is. I'm just told here's a polynomial, solve its x-intercepts. Set y equals 0, right? Just solve for where what x value gives me 0 in this case. We can't really handle this normally, so we're going to use the factor theorem to try and achieve this. What we're trying to do is figure out what potential linear would give us is a factor of this. So how do we actually do that? What you'll typically do is you'll look at the last term of the polynomial, no matter what it is, and every time this is written in the book, there'll be a constant at the end for you to look at. What you're going to do is list all of the plus minus versions of the factors of that term. So plus minus 1, plus minus 2, plus minus 3, plus minus 6. These are all the numbers that you're going to plug into your f of x, so this thing here. These numbers are going to be the stand-in for your negative b over a, right? That's the That's the remainder theorem equation there. Now we'll notice that always condenses down into some integer, at least in these cases. So what we're subbing in is basically at this stage of the equation. It's going in there. Test them in terms of easiest to hardest. So start with the smallest, end with the biggest. Most questions are going to be finished by like, I don't know, anywhere from like 3 iterations down. They're not trying to get you to waste plenty of time, unless maybe it's the textbook. The textbook doesn't seem to have too much concern for how long you're spending on things. But the SACs and exams, yeah, sorry, just the SACs, I guess, because the exam doesn't do this really. Yeah, so we're just going to test them. Chuck it in. If you get 0, you're happy because you found a factor. This is an application of the factor theorem. So this one, we chose the easiest number, and sure enough, it was written in a way where the easiest number was, in fact, a good choice. Here's what it looks like if you choose the wrong number. So if you were to test a negative one, you would get 8. This is not a factor. You would then move on to the next thing in the list. But in this case, we did. So worth pointing out, when we subbed this in, we kind of subbed it in a little bit like after this is simplified. So we had f of 1 is equal to 0. Factor theorem says f of negative b over a is equal to 0. Hence, this is the same as that. We have 1 equals negative b over a. Now that's 2 variables. How do we handle that? We'll talk about the complications later, but for now, pretty much just take for granted that we're going to take a equals 1. There are other circumstances where it's not going to be 1, but in the vast majority of cases that you're working with, it's going to be a equals 1. And we'll look at when it's an issue maybe later. But for now, take a equals 1. That's going to get you your b value. You have a, you have b. You have now achieved your factor. From there, we know this is a factor of that cubic. The whole point now is to go through the polynomial division approach, get your second factor, and then from there, you can now null factor law it. You have the factor you found, you have the factor as per the polynomial division. Null factor law says either this or this must be equal to 0 as far as solving for x-intercepts, which is now actually solvable using the methods we're already aware of. Very long procedure, right? Like, we had to write out our list of these things, test anywhere from 1 to 3 different factors, see if you get 0, reverse engineer that back into a linear, do a polynomial division, split that up into 2 separate factors, null factor law. This is why it doesn't show up on the exam. It's heaps of effort for one topic that they're trying to test. But SACs are more or less a few topics, so that's why this might be in your SAC. Big laundry list of things to do, but it's all there documented for you. I know there was a lot in there, but was there anything in there that needed further clarification? Cool. You find the classwork docs. Okay. Holidays week 2, and that should do it. Cool. So these are the textbook chapters that are covered by what we've just discussed. That's going to take us chapter 4a, 4b, and 4d. The division side of things is probably going to be the toughest of the lot. I'm sure everyone here is fine enough with quadratics, perhaps. We're going to spend the rest of the time, potentially we could do the polynomial division side of things. Any preferences? Okay. Now, you can see that, again, the textbook also has examples of how it's been worked out. They don't use those brackets. Again, you don't need them. It's just there for your own protection. Debating whether to go through rational root theorem. We should probably practice a few before we give that a shot. Rational root theorem basically shows you how to handle when there's another coefficient there. That's that whole thing of where a could be a different number other than 1. But it's so rare of a question that pretty much only the textbook handles it. So I think we could probably leave it there until it becomes more relevant in your actual studies. So let's see if we can take a stab at doing one of these. Do you want to try and do it entirely yourself for one of them, or do you want to try and like go through it live and you guys just tell me what each step's going to be?
Chris, sorry, my laptop
Yeah,
just decided to,
yeah, I saw. All good.
uh, have an attack again. What were you
Yeah.
talking
So I was just basically briefly touching on rational root theorem, and we may or may not touch on it in more detail. But the question I asked was, would you guys want to try and do these questions entirely on your own and tell me later, tell me like at the end of when you solve it? Or do you want to sort of go line by line together, but you guys like tell me what each of the lines going to be?
I'm happy to go like by myself, but obviously it's Vivan's choice
Yeah,
as to
sure.
what.
Yeah, I don't mind either way. Maybe we can do it live, like the first one, and then the ones after we can do it by
Yeah,
ourselves.
cool. Let's stab it. Awesome. Okay, so I guess what I'll do is I'll write it out on the document camera a bit now. So I'll set up the initial thing. We had x cubed minus x squared. I know it's a bit blurry. Oh, no, it's fixed itself. X cubed minus x squared minus 14x plus 24. And the linear we're dividing by is x plus 4. Cool. All right. I'll say nothing for now. What should the first step be?
Would it be getting x divided by x cubed, so it's x squared on the
Yep,
top,
that's it. This one divided by that one, x squared. Brilliant.
and then you times it,
Yep,
x squared times x plus 4,
that's it. Yep. So that's going to give us
x cubed
mhm,
plus 4, no, plus 4x squared.
yeah, there you go. Plus 4x squared. That's it. Nice. What do we do from here?
Yeah, you minus it.
Yep, minus it's correct. I'm going to put the big brackets around it. Hopefully that makes it easier. What's that minus going to look like?
So it'll be minus 5x squared,
Mm-hmm. Anything else?
and then no, then you just write the other two down.
Yeah, that's it. Those are going to drop down. Absolutely. Minus 14x plus 24. Cool.
And
Nice.
then so it's you do the x for x and x squared, actually minus 5x squared, so it will be minus 5x,
Yep, that'll be good.
and then you times it, so
Mm-hmm.
minus 5x squared plus 20x,
Look again.
or minus 20x,
Yeah, minus 20x. That's better.
and then you minus the whole thing,
Mm-hmm.
it'll be minus 6x plus 24,
Try again for that one.
minus 20x plus 24.
Not quite. So this is what I'm talking about. So like with this, right? Minus 14x minus minus 20. So the double negatives cancel to a positive here.
So plus 6x.
Yeah, plus. There we go. Yeah, almost done.
And then you divide again, so 6 plus,
Mm-hmm. Yep.
and then you times it,
Yep. That's it.
36x plus 24, and you just minus this.
Yeah, cool. So that result of 0 there, we're pretty happy with that probably. What does that result of 0 actually tell us?
There's no remainder.
No remainder is correct, yeah. There's a specific word I'm looking for there in terms of like when we're trying to solve a polynomial.
X plus 4 is a factor.
There you go, x plus 4 is a factor. So result of 0 means it's a factor. It does mean the same thing, right? Remainder 0, those are the same thing. Yeah, I mean, you kind of just like walk through that whole thing there. It sounds like everyone here is pretty confident, more or less, with polynomial division. You know, there might get slight complications when you've got quadratics in there. Maybe we'll start looking at more so like applications of it. Like for instance, it seems like in question 6 we're going to start looking at applications of that. 6a should be fairly trivial. It's just using remainder theorem there. Take a stab at, oh, I didn't even pull up my solutions. Take a stab at 6a, and that should lead us into 6b, which looks a little bit more fun.
Is it negative 16?
It probably is. I just got to pull up the solutions. Yeah, negative 16 looks good there. Basic remainder theorem there. Cool. All right, let's see if that actually mattered. No. Okay, B didn't even use it. No worries. Okay, find the value of A for which this string of nastiness is divisible by that, but not by that. So one of the first things you'd want to point out or try to understand is, what is that mess? What kind of function actually is it? Because that'll allow you to hone the direction you start taking your solution. What kind of family of functions do we call that mess of letters?
Looks like a quadratic.
Yeah, it's a quadratic. So typically we think of x as the only true variable, and everything else is just some sort of coefficient. And yeah, the highest power of x in there is x squared, so we would consider this a quadratic. Nice. It's a quadratic, that means it's also a polynomial, which means all of our polynomial techniques now apply to this, and quadratic techniques for that matter. So from there, we've got to figure out how do we make it divisible by this, or like which value of a makes it divisible by this, but not by this. Something is divisible by something else. There's a keyword for that, which should help you figure out what equation would be helpful for this. This one might take a little bit to get through. A bit of plugging in and playing. For anyone who may be still stuck on how to start, divisible by something just means that that thing is a factor of that. So another way to understand the question is to say, what value of a would make this a factor, but not this one being a factor? Keyword factor. Probably going to use the factor theorem for it.
Does A have to be 4?
A does have to be 4. Yeah, brilliant. Walk me through a bit of what you did there.
So with just by recognizing it, right? You can see that if you sub in values for in X, you'll get a quadratic out of A as well.
Oh, yeah.
And then so when I subbed in like X is equal to 2, because negative B on A in that case is like f of 2, you
Oh,
should
yeah,
get
yeah, yeah.
you should get a quadratic A squared minus 7A plus 12.
Yeah.
And for that you get A, and if you equal that to 0, you get A is equal to 3 or A is equal to 4.
Yep, that's good.
And then if you do the same for 1, you get A squared minus 6A plus 9.
Sure do. Yep.
And for that, um, looks like it's going to be like A minus 3 squared.
Yes. Yep.
And so then A is equal to 3.
A would be equal to 3 for that.
So
Yep.
yeah, so then you can't use 3 because they both overlap, and you don't want them. You want it to be divisible by only x minus 2, so that leaves value of A is equal to 4.
Yeah, correct. So you only want one of those to be the divisible bit. So in your solution, you've found what would make them both the same, or at least individually, what would make them divisible. You just want to pick the one that makes one of them divisible, but not the other. To put that into a bit of writing, this is what they've done. All right, these are the two tests for the factor theorem, and then these are the solutions you were mentioning. And then yeah, just pick the different one. Any part of that need further clarification? A bit of a lengthier one. Oh, okay. The right screen share? What do I hope so? Yep. Awesome. These are a lot easier than that. That's just the remainder theorem. And then I'm assuming one of these would have been the factor. So yeah, actually using it to factorize. Yeah, okay. See which one of these was the factor, and then see if you can now take that learning to actually factorize this cubic. So we're doing 7c technically, but you kind of need at least one of these for it. Or not. I mean, you can also just do the whole test the plus minus of the factors here, but this 6 over here is going to make that a bit weird. So probably just stick to these. anyone's still stuck, you would basically be testing factor theorem on one or both of these, or at least until you find which one's actually the factor. And then going through the polynomial division using that factor. Whatever you get at the top, the quotient will be the other factor to whatever one of these is the other factor.
Chris, is the answer to C 2x minus 3 times 3x plus 1 times x plus 2?
That's it, yeah. This one actually ended up getting split into 3 linears. Why do we have linears when polynomial division normally gives us a quadratic after all that?
You factorize the quadratic after further?
That's it, yeah. So the
Mhm.
quadratic that you get after this division is itself factorizable. So I think that's kind of why they put that keyword in there completely. They're trying to give a slight hint to say, hey, you actually need to go a step further afterwards. But yeah, that's the procedure there. Any part of that need clarifying? Because if we're all good with that, I'll go into a bit more detail on the rational root theorem, because that will be a step up from all this. You keen for a step up? Alrighty. Okay, so where do they actually talk about it? Cool, so rational root theorem. Why do we use it? What actually is it? So what we kind of noticed before was in that string of linear factors, one of them had an a value that wasn't just 1. We had like a 2x plus or minus something or other. Rational root theorem is used when you have a polynomial that has a leading coefficient other than 1. So in this case we have 3 as the leading coefficient. As soon as you have a non-monic polynomial, monic meaning it has a leading coefficient of 1, we use an adapted, it's not really adapted, it's the complete version of using factor theorem, where instead of being able to take a equals 1 always, we're now not only looking at plus minus factors of this, which they did list, yeah, plus minus factors of this one, but you're also looking at plus minus factors of this one as well. And what you're essentially doing is arranging them as these being the plus minus factors of b, the numerator, and these being the plus minus factors of a, the denominator. That's how that actually ends up working out, which is why in one of these tests they've done 5, so one of the possible factors here, divided by 3, one of the possible factors from here. So you take the pairs from, or the potential factors from this, and you divide them by the potential factors of this as the thing that you're testing. Now, basically, you have this massive list of things already. Where's a list from before? Where is it? You have like upwards of 8 different things you could be testing. And then on top of that, as soon as this has like a 2 in front of it, you're almost doubling the amount of things that you can now test, because now you've got the fraction versions to test as well to see if they work. So this might give you an appreciation now for why a is 1, because the denominator is actually just factors of the leading term here, but the leading term is always just 1, so the only possible factor is 1. That's the reason why we're actually taking a equals 1 in this circumstance. It's not just a by convention thing, even though that's what I said, just to make things a bit more simple for now. It is, in fact, because when you look at the rational root theorem, the complete version of doing this, the factors coming from here. So that's rational root theorem. You can see this massively expands the number of possibilities that you have to test, which is why it's so very rarely actually in a SAC or an exam. They're putting it in the textbook because it's technically accessible. If your teacher's giving you this I mean, you would hope the fact that it's rational root theorem, so here's like sort of a, you can kind of metagame it a little bit, which is if the question's saying use rational root theorem to solve this, don't bother testing any of the integers, just test the fraction pairs and test the easiest fraction pairs first. Because if rational root theorem wasn't required, your teacher probably wouldn't use rational root theorem for it. So you've got to kind of game it a little bit, otherwise you've got to spend all your time testing things that are never going to work out. And you can see that tends to lead to kind of quite strange results, although they're kind of just going out of their way to make things more complicated. Yes, technically you can use your quadratic formula to factorize this quadratic even further, but we don't do this. This is, yeah, I never see this anywhere. But cool, that's rational root theorem. We won't really give that a shot because it's just more guess and check. If you want to give them a shot in your own time, worth doing just so you can prove to yourself you can actually get the concept. And if you're still finding any trouble with doing that, let me know. Happy to help, or we can even dedicate some time in a lesson to actually doing rational root theorem specifically. But okay, that's that. Let's see. Prove that's divisible for all values of k. It's a similar question, but getting there is going to be slightly different. You'll still be following more or less the same procedure, but the way you're working out is going to... You'll probably see what I mean when you actually do it. I think it's different enough to be worth doing. See if we can go 8a. Oh, actually, no, what am I saying? Yeah, it's not going to be that bad, actually. You'll be able to knock this out real quick. Maybe not. Maybe it is a bit harder. So we're still trying to prove something's divisible. So in other words, prove that it's a factor. So you'd still start with factor theorem. That'll be the first hint.
When I do like factor theorem, it suggests that k should be 1.
It suggests k should be 1. Okay.
Yeah.
The arithmetic might be a little bit off, or the solution's off. One of those two. Why do you think k1?
So when I sub in like -1 into the expression,
Yep.
I got -2k plus 2 is equal to 0, and then that collapses to k equal to 1, but maybe my arithmetic is off.
Yeah, probably double check the arithmetic there. I believe everything should collapse to 0. In the sense like
Yeah,
k.
that's what I would expect as well.
Yeah, k should eliminate itself entirely. Because obviously what you're looking for here is to show that any value of k would work. Obviously, if you get a single value, something's off. I'd be checking around like where you've done your K arithmetic. One should be a plus, one should be a minus. Which probably might be the negative on the brackets.
That's plus though. This
But you're subbing a -1 for x.
right, but x squared on the other one here.
Oh, you had x squared here. Yeah, okay.
No, okay, makes sense.
Yeah, cool. I'll just screen share that one just so we can all be on the same page. Here, cool. So you're subbing the -1, expand, 0. K has been fully eliminated from the equation, therefore all values of K should be fine for that. All right, that brings us to time. One very minor announcement. Even though class 3 is nominally a catch-up class now, a repeat of the curriculum stuff, I did actually misread my curriculum a little bit. So I will be going through the class that should have happened, which I think is a bit of quadratics stuff as part of that. So it is technically more than just a catch-up. So if you wanted to learn from that or otherwise, it's a little bit more than a catch-up than it used to be. The rest should now be fixed afterwards. I've updated the curriculum so it's a lot easier to read. Because what I had done was I'd put the Head Start stuff at the top, when in reality you do Head Start at the end of the year, and I just sort of misread it. So that's all fixed now.
So, Chris, will it be like going back to similar like last year, how we had like 1, 2 stuff on Monday, 3, 4 stuff on Tuesday, and then
Yeah, that's
ambiguous on Friday?
last bit, sorry?
Like like last year we had like when like Pia and stuff were like in class, we used to just like do mainly 3, 4 stuff on Friday, but like it was ambiguous, like
Yeah, Friday was kind of supposed to be a Q&A style thing, but not
yeah.
many people were really submitting things for it, so we kind of made it a hybrid. Now what I've done is it's basically just going to be a repeat of the class 1 and class 2 lecture content as a catch-up for those things.
Okay.
But still feel free to submit things for it. You know, this is still a small group, and
Yeah.
you guys seem like you're pretty switched on, so if there's things you actually want to have a look at, I'm more than happy to override that while we can.
Cool.
Otherwise, yeah, I'll stick around for a little bit if there's any further questions. But otherwise, yeah, take care, guys.
Yeah.
Thank you.